more like transformations. So remember, we talked about that already, about linear functions and how they work as transformations, but you don't really see the possibilities. How linear functions are very simple, but yet they have they're capable of doing so much, and you don't see it until dimension 2 by 2. So functions are, you might remember something like this. So a function, the domain, the codomain, and this is where things starts to become interesting. It is when both of the dimensions are 2. Okay, remember it is I illustrated with taking a piece of paper and placing it on the surface. Okay, so with a variety of transformations that precedes it. So you can collapse it to a point, to crumple it together into a point, or you can wrap it around an axis, and all of that. Those will be functions. But okay, so that is the starting point. And then, unfortunately, beyond dimension 2, dimension 2 by 2 it can still be illustrated. So that's why we will spend some time doing this, because it is the features of those functions that we discover. We can still match them with something tangible, something that we can see on a piece of paper. Okay, so this is what I mean. So you can do things with Excel, as you can see. So it gets harder. So if you've seen any well, you have seen some visualizations of graphs in calculus. So what is the x-axis, y-axis, and you have a graph of a function. That's it. So in other words, that's what you see in calculus 1. F from x to y, dimension 1 here, dimension 1 there. So that's calc 1. Okay, and the visualization is very simple. That's visualization, x and y. The input is one-dimensional, output is one-dimensional. Okay, so the challenge here is, how do you visualize it? How do you visualize it when both of the dimensions are, both of the spaces are two-dimensional? So it's a plane to a plane. It's like this. So every point here will somehow find its new place over there on the other space. So this is x and this is y, and this is my f. Okay, so so that's a challenge. Sometimes it works out, and that's the example I'm showing you. As you can see, what has happened. What do you see has happened here? One plane, the other plane. So as you can see, the point is, the only way to figure out what's happening to the plane on the left is transform to the plane on the right. The only way to figure out what is happening not to keep that piece of paper blank. Draw something on the piece of paper and then see what happens to that drawing. So that's what I did. I drew a bunch of concentric circles on one piece of paper, and then after the transformation, what has happened? Expanded, yes. In fact, they expanded uniformly, right? So what?
Everything doubled.
Everything doubled, right? That's right. So you can see it right at the top. At the top, F is our matrix in pink. It has 2002. So that's the matrix 2002. Turns out to stretch everything by a factor of 2. Okay, so that is easy to demonstrate, so let's do it. So our matrix, say, F is 2002. Let's confirm that indeed it stretches. So say X is equal to, well, let's abandon those things. X is XY. Okay, and then, well, let's compute fx. So we have 2002 multiplied the usual way, xy. What do we get? So multiply the row by the row. There will be how many entries? Two entries, right? So this is 2 by 2, and this is 2 by 1. So the result will be 2 by 1. If you remember this, how this cancels out, and you have 2 by 1, and the result is 2x, 2y, which, if I want to use vector algebra, what is it?
2 times
xy, that's right. So that way, indeed, we discover that fx is equal to 2x. Okay? So it turns out this matrix 2, 0, 0, 2 it represents nothing but multiplication by 2. It is a scalar multiplication of vectors, and the vector gets multiplied by 2. So that's the conclusion that we derive. Okay? So it just happens to be very simple example, but that's how you start. We'll do a couple of examples to see what happens. So well, it is very easy well, okay. So what if I put 1 here instead of 2, 0, 0, 2? I'll have 2, 0, 0, 1. If I put 1 over here, you see where I'm putting 1? Right there. What do you think is going to happen? It will be disproportional, right? So you'll have a stretch, but only horizontal, not vertical. So okay, right? So once again, a piece of paper with concentric circles drawn on it has been transformed, and they turn into ellipses. That is much harder to illustrate algebraically. Okay, the way we did it here, when everything is uniform, that was easy. But well, I guess it's worth describing. So f equal to, given by 2, 0, 0, 1, stretches the plane horizontally. Okay, what about this one? What if I put 0 there? If I, instead of this 1, I put 0, what's going to happen? Exactly, the result will be a line. You can see it almost, but you can see wherever these circles went, they are all within the x-axis. Okay, but you can imagine what the difficulty is where the simplicity comes from. Why it was predictable. The reason is because the only non-zero entries in our matrix were on the diagonal. So x's went to x's, y's to y's. There is no mixture of x's and y's, right? So that is still visible if I go back here. So if I look at this matrix, so 2, 0, 0, 1 multiplied by xy, what does it give me? It gives me 2x, y. Okay, so you can clearly see non-uniform stretch. But if I put an extra number elsewhere, so 2, 1, 0, 2, for example, then that extra number off the diagonal is what creates a problem. It makes things unpredictable, and in fact, it's pretty hard to. I don't think I can tell if I still put 2 here, okay, but if I put 1 there, well, you can't predict what's going to happen. I think I know what's going to happen. Can you tell what's going to happen? Well, there's a stretch. What else? The stretch will probably still be present. What else?
Will it be a diagonal stretch instead of a normal x or y?
Well, that's one way to look at it. Yeah. But is it a diagonal stretch, or is it a stretch followed by a rotation? Or is it the same thing? Kind of. You certainly look at those circles and you see that they've been stretched diagonally. And by the way, do they look like they stretch 45 degrees? They seem a little bit off. But there is really no reason to be off. Okay, so that's what happens. So we have to break it down. Then that's the way to analyze functions, is to break that down into. That's why it is better to. Well, actually, we have to do both. We have to break it down into consecutive operations such as stretch and rotation, or we could, if we can see that it is nothing but a stretch in a particular direction, that could also be an option. So what is missing right now is in fact rotations. So let me give you one rotation that is kind of obvious. Well, you can actually probably can tell me the rotation 90 degrees. 90 degrees. Counterclockwise.
2202?
No, we're starting from scratch. So if I have xy, what is its perpendicular? Well, we'll figure out what the matrix is. It's easy. Once we have the formula, we can figure out the matrix. That's no trouble. So I just want to, what is the formula? What is the, if this is my vector is xy, right? What is this?
The inverse?
No, not an inverse. It's 90 degrees, so. Close. Yx. Remember, what is the relation between these two vectors supposed to be? When they're perpendicular? The dot product is 0, so is it?
Yeah.
No. Xy times xy, one vector, the other one yx, dot product will not be 0. What's missing? The negative sign somewhere. So let's put one here, then the dot product is 0. The only thing that might be an issue is, are we rotating in the right direction? Is it clockwise or counterclockwise? So it appears to be, so x is negative. It appears to be correct, right? So this seems to be a rotation of 90 degrees. Okay, so as you can see, the logic was different. Rather than starting from a matrix, we started with the what we wanted to accomplish, and then now we have a formula. Let's find a matrix. It's really uncomplicated. So what is the matrix for this transformation? So what is the matrix to insert over here? So that the result of multiplication by xy will be negative yx.
-1. Wait.
No.
Negative y over x.
No, there won't be any x's and y's. So matrix will be simply 4 numbers.
0, -1.
I think so. 0, -1, 1, 0, I believe. So if you want to verify it, you multiply, so 0, -1, 1, 0, multiplied by xy, right? So what is it? It will be x times 0 plus y -1. Okay, it's negative y, and then I have 1, and I have x times 1 plus 0 times y, and that is x. Okay, so that works out. Checks out. So this is the matrix of rotation. As you can see, those off diagonal elements is what they create rotation. So the diagonal element, well, at least when you keep them separately, as you can see, this is this, and that on one hand, not this one, sorry, these two. So stretches, depending, there are 2 entries, and then there are 2 stretches vertically and horizontally direction, and as long as the other entries are zeros, that's all you have. You have 2 stretches, okay? And then, but on the other hand, if you keep the numbers on the off the main diagonal, so main diagonal is what is it, southeast. If the other one, you have entries, then those will be giving you rotation. or at least so far, as you can see, you express what has happened is we express x in terms of y, x in terms of y, and y in terms of x. That's how it works out. In general rotation will have to be more complicated with all four entries involved, because x will depend on x and y, while it depends on x and y as well. So far that's all we've got. But at least we have a rotation, and if I try to do what's going to happen if I put, well, if I put 0, 0, 1, -1, and 0, what's going to happen? What's going to happen to the picture? What's happened to the picture? Yeah, the picture is the same. Right, so we know we have rotated it, but those circles are they're circular. So that's the problem with high-dimensional things, that a certain approach might give you only part of the information. So if you start with circles, then the rotations won't be visible. Okay, so there is another. So what it means? It means that try to draw something else, not a circle. So something that would be visible as you rotate it. For example, I have here. You can draw an ellipse. So let's draw an ellipse. So the left is the ellipse that I drew by choice on my original xy plane, and then I put here once again 0. Oh no, that's not 0. This is 1, 0, 0. Okay, so you see it, right? Rotated, that those ellipses have been rotated 90 degrees. Okay, so that worked out. So the formula, the general formula for rotations will have to be sorted out. But we have seen almost everything that can happen. So we have had stretches, non-uniform stretches. We've seen rotations as well, and we saw collapses. We saw collapse on a line. The only thing we didn't see, but there is nothing to see if we collapse it on a point. There is only one operation like that. The zero matrix will simply collapse. Okay, let me first describe this. So the collapse, or projection, that's what it is. In fact, collapse may be too strong a word, but it is what this is, a projection on the x-axis. So that projection that we have talked about, projection, vector projection. Okay, so vector xy has become, well, this one is projection and a stretch, so we don't need that. Let's make it pure projection. So 1, 0, 0, 1. What happens to the vector? Xy goes where? We will go to x. I'm sorry, x0, right? So that's a projection. Vector xy goes to vector x0, so the y component disappears. It's projection on the x-axis. But you can have projection on other axes, so that's the difficulty of these four main things. So projection, stretch in different directions, rotation. Okay, so these three may be combined in different ways, but they can also be conducted in different directions. So for example, you could stretch in x direction and y direction. By why so? Maybe you're stretching in some random direction that you don't know ahead of time. So you only have four numbers to worry about in your matrix, but yet how many things can happen? So you can stretch this way and that way, and stretch this way, shrink this way, and then rotate. Well, rotation is just one number, but still that is a difficulty. Even if you do in projection, you can imagine that we can do projection on anything. We can project it on the, say, diagonal. Can you think of a projection? A projection on a line x equal y equal x. So these are my x's. This is my line y equal x. I have my vector like this, xy, and this is the projection. So can you think of how to find it? 90 degrees, remember? Well, actually it's not. So let's make it an exercise. The answer is not obvious. So let's just start on this and analyze the whole thing now. So these are just examples of the two-dimensional situation. As you can see here, there are certain characteristics to the right of the matrix. There are certain characteristics of that matrix that tell you what's going on without looking at the picture. And those characteristics, as you can see, the determinant, the trace, and the eigenvalues are the ones that tell you that. And in dimension 2, you can see those identifying characteristics. You can see them on the picture and match them. In high dimensions, these are the numbers that you will have to rely on because you cannot visualize. Okay, but so far so good. We can visualize them. Okay, so we'll get to that. But with the understanding that functions are matrices are functions, and linear functions are matrices. That's with that understanding, we'll just go on. Okay, so there are certain things that we need to discuss. Well, for example, to begin, what does it mean for a function to be linear? Without saying that there is no trig functions there, that doesn't do it. So we have to understand that in a more positive way rather than negative way. So we have to understand linearity, and where this starts is the linear combinations. We already seen them. So remember what they are? And so x, y are vectors. What is their linear combination? Well, you can describe it as verbally as the sum of their multiples. So ax plus by. That's all. Y, capital. Okay, so A, B, just two real numbers. Okay. Okay, so do you remember from before where we saw these? Well, let me make a picture so that might refresh your memory. So if I have vector x here and vector y there, okay, so the multiples say this will be 2x, and then I have 3x, on and on. Negative x here, this is, by the way, 0, the origin. This is negative y. This is 2y. So I'm writing the multiples of these two vectors, right? Negative 2y. So then the multiple of, so suppose we only worry about one vector. If we take all of its multiples, they form what? A line. So each multiple, no, not each multiple, the multiple of each vector. So the set of all multiples of a vector, not 0, is a line. You keep multiplying, 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 you have a line. Okay, so that's the starting point. Now we have two of those. Okay, two lines, and we are allowed to add one vector to the other vector freely. Not only I'm adding x to y, but I'm adding also x to 2y. And I'm adding 3x to 2y, and so on. All of these are possible, so let me That's a lot, actually. It's a lot. So, for example, this one will be here, and that one, and this one. So if I just take the integer multiples only, I'm already getting a lot of stuff. All of these were points that are placed the end. They are the endings of vectors. Okay, this one too, and that one too. So together they form a plane, right? So the sums of the multiples of two vectors form a plane, unless what? Yeah, already indicated that they're not, well, okay, well, yeah, so to begin with, not 0, right, okay. Both of them not 0, but is that it? What?
Parallel?
They're not parallel, which algebraically we express how? Not multiples of each other. If you think about it, then, I mean, if you take multiple of x, multiple of y, if they're multiples of each other, so then we're not adding anything. I already have all the multiples of x there. So if y is a multiple of x, then it does not contribute anything. So I'm still with a line. Okay? So, so from a line to a plane then. And you can imagine that you can go down that line, hypothetically, if you add a third vector. So you can still speak of linear combinations. So x, y, z. So a linear combination, or all linear combinations. So say I have three vectors. So I have a x plus by plus by plus cz. They'll form what?
Space.
A space, yes, a 3D space. But once again, under certain restrictions. What are the restrictions? Well, they still cannot be multiples of each other. Otherwise, it's going to be a line again. But that's not enough. It could be a plane. Under what circumstances it would be a plane? What?
They're all parallel. They're like.
Right, but that's multiples of each other. That will be a line.
They're all in the same direction.
Right. Well, that's the issue that you confront here is what we need to deal with. They would not have to be. I don't know if I want to write it down because you have to explain linear combinations in terms of other linear combinations. You have to say that not only none is multiples of any other, but also no three of them lie in the same plane. But what is a plane if not a linear combination of any two of them? So it's really not productive just to look at it one case at a time. So that's why we're gonna build up a theory here, and that's the theory is based on the idea of linear combination. So once again, a linear combination of two vectors is simply the sum of all of their multiples. Okay, so once again, remember where we saw this picture before. So just to explain why we care. Remember seeing a picture like this? Recently.
You drew on Excel.
What?
You drew it on Excel. Didn't it?
No.
It was kind of like this.
No, it was recently about when we were doing systems of linear equations.
You're
Remember?
talking about the Excel?
No. No, I'm talking about solving systems of linear equations. Where's the thing? Here. Okay, suppose we had a system of linear equations. We found its reduced row echelon form. We put the answer in this vector notation, which is way on the right. So this is my vector notation for the answer. So two vectors t and u, v and u are given to us. They come right from that solution, right? And then what have formed there? Look at it on the right. I have formed their linear combination. So those two parameters that appear on the left, especially as what is as free variables, t and s. Those are free variables from our system of linear equations, and we just renamed them for our convenience, t and s. But they're numbers, and they at the end of our solution, they serve as multiples of those two vectors v and u. Vectors v and u came from our reduced row echelon form as certain columns in that form. Where is it? Here it is. Certain columns, vectors are columns, and so those vectors -1, -2, 1, 0. That is my v, and my u is -1, -2, 0, 1. And then, so they just dropped in our lap once the system has been reduced to that form. And then turns out the rest of the, turns out that all the solutions can be represented in that fashion. TV plus SU. Once again, I am dropping out S so that it wouldn't stand in the way. So this, I dropped this. And then the end result is indeed a linear combination is visibly the sum of the multiples of two vectors. So it is very similar to something very even more familiar from a long time ago, and that is I and J. Except, so here you know what I'm talking about. I and J is the two basic vectors in the Cartesian system. So every vector then is a linear combination of those. And those. So I guess we gotta move on to make that point clear. So as an example, the basic example, I suppose, is that any vector in R2 is a linear combination of I, which is 1, 0, and J, which is 0, 1. Okay, so how? Well, it's very simple. So if I have 7, -3, it is a linear combination, 7I plus -3J. Okay? So the only difference is now, this is really too simple. As you can see, there is no restriction anymore in what way that I and J were perpendicular. So that's the thing about IJ. They were unit vectors to begin with, but that's really not as important as the fact that they are not perpendicular anymore. So those vectors x and y, when we're talking about linear combinations, that don't have to be perpendicular, and linear systems is where it comes from. You solve a system of linear equations, you end up with those two vectors, maybe three, maybe more, and then turns out that the solution set is the set of a linear combination of those vectors. So let's have a simple example. That was four-dimensional example, so maybe it was excessive. But let's well, actually, yeah, we got to do it in high dimensions, as a matter of fact. So, well, but let's write it out. Let's write it out. So, a homogeneous system. So let me write system so we don't have to go back to that notebook. And so say x1 plus nothing, plus 2x3 plus 1x4 equal to 0, x2 plus x3 minus x4 is equal to 0, x3, well, there's no x3. Okay, so that's our system. Okay, so that's what's left of our system, and then we form our explicit solution, which is x1 is equal to x2, x3, x4. Well, tell me, what should I write here? In analogy what we just did, or we just saw. So reduced row echelon form, right there. What should my vector solution be? Or it's not the vector solution yet. Remember this, so these are the free variables. What do we do with the free variables? We rename them. So they would become those parameters, those multiples. Okay, so it will be t and s. And now x1 is, and everything is then expressed in terms of t and s. So what is x1? Minus s. And the other one is negative t plus s, is it? Right? Okay, so so we're moving this way, and then we write it in the vector form, so that my x1, x2, x3, x4 is expressed as a linear combination of what? A linear combination of the vectors that to be determined by the multiples will be t and s. T times certain vector plus s times certain vector. Okay? You just go along those equations and collect what you need. So from the first equation, what do I put here? Negative 2, then down negative 1, 1, 0. Okay, and the other one will, for s, will be what? Negative 1, 1, 0, and 1. Okay, so these are the two vectors u and v, but we can call them x and y if you prefer. But the formula speaks for itself. These are the linear combinations. Okay, so whatever t is, whatever s is, we have a solution. Okay, so as you can see, remember that caveat, there will be a plane if they are not multiples of each other, and they are not. So which means that indeed that this is going to be a plane. Okay, so x and y are not multiples of each other, so their linear combinations will form a plane. So it will be a plane, so R2 in R4. A copy of R2 in R4. Okay, so in a way here u x and let's drop these x and y serve as what? They serve as the role of these play the role of I and j, because every element, every solution of our system can be expressed as a linear combination of these two. Okay, even though they're not perpendicular, we don't care. Okay, so that's where the real source of that idea why we care. So these are linear combinations. Okay, so and that is what's behind the idea of this, the idea that I just said, a copy. So why would I say it is a copy of R2 while it is not? It's certainly not an R2. For one, we don't even have I and j. If we're talking about R2, there should be those two basis vectors, I and j, and we do not have them. What we have is just this expression. We have two vectors that are not perpendicular to each other. You can certainly verify it by dot product. They are not perpendicular to each other. So x not perpendicular to y. Okay, and yet they still can be used. So that's the bad news. The good news, they are not multiples of each other. So the point then is that we still can, based on this idea that they are not multiples of each other, and we're talking about all of their linear combinations, that is the idea of what we want to say when we want to say that R2 and R4. We're looking something that is not R2, but it is close enough to it so that to identify it as a plane. So, and a plane has to match somehow with R2. Okay, so that's how we want to classify all possible outcomes of solving systems of linear equations. Remember, those in dimension 2 it's easy, but in high dimensions it's just so many possibilities. And so we want to establish that relation. And so this is how we go about it. We define what's called a subspace. So a subset first. Well, I don't have to explain what a subset is. Say V in Rn is called a subspace. Subset is a subset, a smaller set. Do we need to talk about that? Subsets? No? Okay. So a subset of these is called a subspace if the following condition is satisfied. X, Y belong to V, then AX plus BY, a linear combination, also belongs to V. Or any real AB. So in other words, for any two vectors in V, their linear combination is also in V. So that's a verbal description of what it means. So that picture, this picture shows you what I'm talking about. So so imagine that picture that we're looking at is in a 3 or high dimensional space. Okay, so it means that, well, there are 4 independent directions, and then we picked what we did. We picked and then we want to understand what the meaning of a plane in a high dimensional space. What does it mean for a subset of a high dimensional space? Let's say 3-dimensional space. What does it mean in vector-wise? How do you explain that a plane right here will be well, a subset, some subset of the 3-dimensional space? How do we explain that it is in fact a plane, not I don't know, a paraboloid? That's how. So this is, suppose we are talking about the 3-dimensional space. This is the origin. Okay. So x's don't really matter. X's or basis vectors, they're really not part of this. So how do I know that this is a plane? That's how. If I take vector x and y. Okay. So once again, I take x and y. Any two vectors x and y originating from the origin. From the origin O, so this is x and this is y. Okay, if I add them together or add there any of linear combination, I will not move out of this plane. Okay, so you can imagine, so this is x plus y as a particular example right there. So, well, let's have an example when you can certainly imagine that if I drew 2 vectors on this board, and then add them together, or any linear combination, their sum will be still in that plane. We've seen that so many times. But try to imagine when this is not satisfied. Under what circumstances a subset of a say 3-dimensional space is not a plane? But high dimensional. Verify the condition. So, for example, if I take what? Well, if I take these, so 3 vectors, my subset V consists of exactly 3 vectors like this. Okay, then what's going to happen? If I go linear combination of these, well, I probably should find a better example. Well, let's look at the simpler question. The simpler question is once again just multiples. Okay, so as you remember, the b could be equal to 0, which means that the linear combinations also include all the multiples. Okay, so just like in that picture. Okay, the multiples also have to be there. Okay, so that is why. Where's my picture? Yeah, multiples. It has to include the multiples as well. Okay, so which means that our subspace would have to contain all. If it contains a vector, it contains a little line through that vector. Okay, so anything curved is out, right? If I have a curved surface, say sphere, it's out of the question because the vector could if it is anything like this. This is my vector. Then the multiples of that vector will not be within the my curved surface anymore. However, you could say if I take one line, 3 lines, 5 lines through the origin, they will satisfy that property, right? It is where the addition comes into play is when the trouble starts. For example, if I take all the 3 as an example, I'll take the 3 axes. So suppose this is my V. V is made of the 3 x's. Okay, so once again, if I start with a vector anywhere here within V, every single of its multiples will also be in V. However, if I take 2 vectors, this is along x and along y. This is along x. This is along y. Along y. Okay, so if I add x to y, it will be out. So this is x plus y over here, pointing away from the x's. So in other words, if my set V contains the x-axis and it contains the y-axis, what else does it have to contain? The xy plane. Because, as you can see, so the adding x on the x-axis, y and the y-axis will produce something pointing possibly in a diagonal direction. If they're equal, it will be on the diagonal direction. Otherwise, it might have any direction. Okay, so that takes some time to talk about.